we want to try to get this thing going, and we want to make it fast, and we want to make it better. So we have something going now that we just need to optimize, and how to put it along. I'll pass over to you.
All right. Is that everyone?
So you're happy to do this is what Tracy Yeah, I'm not sure. I followed the book that approach that I think that's
All right. All right. Welcome everybody to another week. Hello everyone online. It is our 5th week now, which means we're halfway through, or almost halfway through, and we're on to our 4th sort of lesson from the course. One thing that is worth noting, as we just discussed before, we are sort of tracking along with the videos that go along with the course. Obviously, a lot of those videos sort of overlap between notebooks. They might not quite finish a notebook, and then you get 1.5 in the next lesson. So the requirements each week is really, if you can focus on that course video, that should cover everything you need. But just like Jeremy did, we'll probably also overlap with bits and pieces so that things sort of make sense. So cool. So today we're talking, following on from sort of lesson 4 of the course. This one is, we're joined by Huen and Tan to come share some content with us and share the workbook. We'll talk a little bit more about some of the group work at the end as well, and sort of how we're going to help you guys as mentors. So guys, if you want to come and start presenting, come join us.
Good evening, how are we tonight? Doing well? Yes, excited? So my name is Huen, and this is my co-presenter Tang. And I did the first Fast AI course about 4 years ago, and the second part in 2018 with some of the people in the room tonight. So it's really great, to see, these people coming back and, helping create the next batch or mini batch of, deep learning enthusiasts. So, so today I'm going to cover some of the, theoretical, background of lesson 4. And before you start running screaming, let me reassure you that this is a really important lesson where everything comes together. And if you understand this lesson, it's going to make the rest of your journey really, a lot easier. And also, I would really hope that maybe, by making this this session very interactive, I can help you build a little bit of the mathematical intuition for what is happening behind the scene, even though the focus of the course is on being practical. So in the first 30 to 40 minutes, I'm going to run through the slides, and then in the second half, Tang is going to do a short live coding session. So for the first half, I strongly encourage you to be really interactive. Put your thinking hats on and close your laptops if possible. We will focus on the material, and we will worry about the computer and coding in the second half. So the key concepts that we are going to cover tonight are cross-entropy loss function, backpropagation, stochastic gradient descent, midi-batch, the learning rate finder, and fine-tuning. And the material will be mostly based on Notebook 4, the MNIST basics, and a little bit of the last part comes from Notebook 5, and there was some comment on the Discord channel that some people didn't have time to go through Notebook 5, and that's fine. We will go through everything, through all the steps in the first half of the course today. So if you recall the 4th notebook, So Jeremy initially proposed a baseline model to basically classify whether an image is number 3 or number 7. And the model is very simple. He basically takes the average of all the number 3 images and then all the number 7 images. And if you have a new image, you just compare that to these average images. So really, it's a little bit like a template matching algorithm. What can possibly go wrong with this model? Yes?
So if the number you're trying to infer is not centered, it's not going to work.
Yes, exactly. So that simple algorithm is extremely sensitive to the exact location or the orientation of the digit in your test image. And in the last lesson, Olga raised the question of whether that can be a useful baseline model for the cats versus dogs task. And she showed us that, the average of all the cats images is this faint face of a cat, but it's clearly nowhere good enough for us to do, this task. And somebody raised the point of, okay, so if we have the cat versus dog problem, what is a good baseline model? And I think I thought a little bit about that question. And I think it goes into a deeper question of when is deep learning an appropriate tool, right? Because as we know, deep learning is very expensive. It takes a long time to train, it's finicky, the training is, not guaranteed to work. So how do we decide when a problem is appropriate to use deep learning? So to drive home this point of why is it that this 3 versus 7 and the cats versus dog problems are really different, I will take a quick detour. So what I did here is that I apply dimensionality reduction on the MNIST data set. So basically what dimensionality reduction does is that it reduces your data from a high dimensional space, in this case, 7 something dimensions, into a lower dimension space, so 2 dimensions, right? And you can see, so in here, the algorithm that was used was called t-SNE, so it's a nonlinear technique. And you can see when we apply that on the MNIST data set, the number 3, so the data points that represent the number 3 images and the data points representing the number 7 images are quite far apart. So it gives us an indication that these images are quite different, are quite separate, and that's why it's a fairly easy task to do. Now the question is, can we apply dimensionality reduction on ImageNet? Can we apply it?
We can try.
Can we apply it directly, straight away? What will be a problem? The number of images. Why is it a problem?
Well, you've also got a large, we've got like 9 images, 9 numbers there, numbers, right? How many images in the ImageNet database? Number of categories? Yeah, number of categories, right?
It should not be, it's close, but it's not really the problem here. So let's say the cats and dogs problem, you only have 2 categories, right? And you have a few thousand images. So is really the number of images a problem?
Is it one's colour and one's black and white?
Not quite. So another answer here is whether color or black and white is a problem. Yes?
Too many pages to reduce.
Yes, yep, that's exactly it. So the answer here is the number of dimensions. So if we recall the ImageNet dataset, each image has a dimension of, say, 200 by 200 pixels, and you have 3 channels. So each image has a dimension of 200 times 200 times 3. That's 120,000 dimensions. So you simply do not have enough data points. And this problem here is called the curse of dimensionality, when you have way too many dimensions compared to the number of data points that you have. So in order to do some sort of dimensionality reduction, you need to run the ImageNet dataset through something else first, to first reduce the number of dimensions to something a bit more manageable. And actually the way to do it is to run it through a neural network. And so somebody actually did that, and he extracted the 4096 dimension features output from a CNN of the ImageNet, I think, or maybe a similar data set. And then he used those features in a lower dimension as input into the dimensionality reduction algorithm. And what he ended up with was this quite interesting, map here. So this 2D map here basically preserves the distances between the different images in higher dimensions, and it's very small. So if we zoom in really, really, really many times, oops, I've lost it.
Click again.
Then we start to see patterns in this clustering. And you can start to see, it's grouping things together like bridges and fences here. And if we go down, you start to see a group of people close together. So definitely the neural network is picking up something here, even though you can see the images, are highly varied and different. So this example here talks to us about when is it appropriate to use deep learning. And the difference between the 3 versus 7 task and the ImageNet task is that the 3 and 7 task is quite low dimensional, really, compared to the ImageNet, where you have very highly complex data set. So normally when you have a problem where the data is quite regular, it's quite predictable, then maybe deep learning is a bit of an overkill. Whereas if your data set are highly different and they are complex and variable, then that's where deep learning is an appropriate tool. So I give you an example of a few years ago, I was given a task to come up with an algorithm to basically detect the location of a latch on the top of a train, a moving train, so that a robot, can locate the latch and then open the door so that, stuff can be loaded onto the train. And my colleagues immediately said, okay, let's do a deep learning solution. The problem with that is that deep learning is slow. So by the time that the algorithm decided where the latch is or detected where it was, the train had already moved past. So that was a huge problem. And then I took a step back and I thought, is this even really the right tool? Because the latch looks extremely consistent, it's really just a fixed object moving across, your camera. Like, why not just do template matching? Tell your computer what a latch looks like, and then it will pick it up from the image, and that is hundreds of times faster. And that is an example of where deep learning can be the wrong solution. So you need to think about when is it appropriate and understand the nature of your problem. Yes.
No, I totally agree with you, but an argument that some people would make is that you train your model once,
Yes.
and then you keep using it.
Yep. So
In terms of speed, like if you do it, you pay obviously for the training phase, but then you keep using it and it can be as fast.
yes, but I think even in production, it can sometimes still be not fast enough because you still have to run the forward pass, through millions of
It could
parameters.
still be 50 to 100 milliseconds, whereas OpenCV could be a couple milliseconds.
Yeah. So in the remaining presentation, I'm going to walk you through all of the steps in training a neural network. And if you went through the notebook, you saw that Jeremy sort of went back and forth. So I really hope to go through all the steps in sequence. So really, there are these 5 key steps here. So first, you have to initialize your model. That's the step here. You use the learner class. And then all these remaining steps really is part of the fit, method. So for each image, you run an image through your network to make a prediction, and then you measure how good your prediction is, or calculating the loss function. And then you calculate the gradient of the loss with respect to all the weights. And the gradients will tell you how to change the weights. And in the next step, you update the weights and you repeat these 4 steps, until you are satisfied with the performance of your model. But before we can do any of that, first of all, we need the data, and we need to load it into a data loader object. And then in step 1, you initialize the model. So you can either create your own custom-made model using this pretty basic class here, learner. And then you can define your own model, your loss function, your optimization, and then the metrics that you want to track. Or you can load a model of an existing architecture. So in this case, the ResNet 18 architecture. And the pre-train parameter tells you whether you want to use the weights that have already been trained on ImageNet. So what are the benefits of transfer learning, of using an existing architecture? Yep, sorry?
Because when they firstly the neural network learn, they would learn the basic stuff like orthogonals or so basically all the neural networks that learning the same thing for the very first about, let's say 10 a layer or something, and then that's why if we use the pre-trained model, then we can save time with doing all the basic stuff. We just move from there and then apply into our data set.
Yes. Yep. So basically, the main advantage of using an existing architecture is, taking advantage of what already, exists. And I mean, training these models can take a lot of time. So if we can save some of that time, it's great. And also, research groups around the world, spend many years to actually perfect and find these architectures that work well, that train well. So if they exist, then we should make good use of them. But when is it appropriate to use transfer learning? Yep.
When your data is similar to the data it was originally trained on.
Yes, correct. So it's appropriate when the domain of your data is quite similar to the data that was used to train the existing architecture. So for example, if you're looking at medical images, you might not really benefit that much from using something that was trained on ImageNet, because the nature of natural images is very different from medical images. But it might work sometimes. It's just a matter of experimenting. So in step 2, once we have initialized the model, then we use the network to make a prediction. So in this very simple architecture here, what Jeremy did was that you just do a matrix multiplication of your input with a weight matrix, and then adding a bias term, and then you run it through a ReLU function, which looks like this, and then another linear layer. So why do we use a bias term in these linear steps here?
If your x values are 0, then you've got the weights don't make any difference.
Yes, that's correct. So we have a bias term, really, to keep all the flexibility of a linear model. And why do we want to include a non-linear step, the ReLU? Can we have someone else answer this question? Yes.
So if we try linear, it doesn't matter how deep we go, you can't create a complicated enough function for us to predict complicated tasks.
Yes, that's correct.
That's what makes it non-linear.
Yep, so the answer is, when you stack many linear functions on top of each other, the output is still a linear function of the input. And if we recall the universal approximation theorem in the first class, right, we want to approximate any function. And any function means it can be either linear or non-linear. So we need to introduce non-linearity to be able to achieve that. And what is the advantage of the ReLU function? Because many years ago when I started doing deep learning, it used to be something else, not ReLU. So what is the advantage of a ReLU function? If you look at the shape here, yes?
Would always be between 0 and 1 instead of having to wait into negative numbers.
Yes. So the main advantage of a ReLU function is that basically the gradient is extremely easy. It's either 0 or it's 1. So it makes your calculations very simple. And once we have the output of this network here, we actually run it through a sigmoid function to get our prediction instead of using the raw output. Why do we use a sigmoid function instead of a raw number? Yes?
Because it's a smooth function that can give a loss value used to inform the next step.
Yes, it is a smooth function, but I mean your raw output is also, you know, it can be a smooth function as well, right?
Can be between 0 and 1.
Why is it important to be between 0 and 1?
Because we want to classify it
Yeah.
a specific process.
Yes. So really, I mean, we want to make a prediction of what our target is, either 0 or 1. So we want to have a probability, right, prediction. And also, the sigmoid function is smooth, so it's something differentiable, and the derivative is quite easy. And also, I think that there's another advantage to this function, which is that you see that its tip is here in the middle. So this is where your prediction can go either way, right? And this is where you really want your learning to happen. You can be right or wrong here. Whereas it doesn't really matter too much that you are 90% sure that this is a cat or 95% sure that it's a cat. So it's flatter out here. So I think that's another advantage of the sigmoid function. And then once we have our predictions, then we want to calculate the loss function, which means how well our model has predicted the inputs. So if you recall, you know, Michael's explanation 2 weeks ago, what is the difference between the loss function and a metric? I'm just testing if you were awake. Yep. Nope. Yes, differentiable. And anything else?
Losses for the model for training, and metric is for humans to understand.
Yes, correct. So a metric is something that we humans might be interested in, whereas the loss function is something that the neural network, you know, uses to improve itself. And so for a binary classification task, the loss function that we use is called the cross entropy, the binary cross entropy, which has this form here. So it's the sum, and I forgot a sum sign here. So it's the minus of the target times log of your prediction, and then plus 1 minus the target log of 1 minus your prediction. And then you have to sum this over all of your data points. And this formula looks a little bit mysterious, and you might think, you know, why does it look like that? And I just want to give a little bit of intuition of why it has that form. So the probabilistic interpretation of the loss function. So if we, just as we discussed before, we can think of the output of the network as the probability that your input belongs to class number 1. So the probability that the target is 1 is y, and the probability that is 0 is 1 minus y. So really we want y to be as close to t as possible, right? We want our model to predict the right class, right? So if we think, so the likelihood function measures how well your model predicts the observed data. So basically you just multiply all of these probabilities together. So it has this form here. Actually, these two equations are exactly the same as this equation here, if you think about it. When t equals 1, this term here becomes 0. So this term on the right becomes 1, right? So you only have y left, which is this. When t equals 0, then this term becomes 1. So you only have 1 minus y left, which is this formula here. So really, this is the more compact form of how you measure, you know, the probability of getting the correct class. And then it's equivalent to the exponent of this thing here. And if you remember from the previous line, this is exactly our loss function, right? So what you're trying to do is basically maximizing the likelihood of getting the correct class. And it's the same as minimizing your loss function, which is this term here. And if you're familiar with information theory, you know, this loss function is basically, you can roughly think of it as the distance between the empirical distribution of the targets and the probability distribution of the outputs of your model. And if you want to know more detail, you can talk to me about that after class. So once we have our loss function, we want to minimize that, right? Because we want to maximize, our likelihood of getting the correct class. So what we do is we do gradient descent. So you can think of gradient descent is you're walking on a mountain, in the fog, and what is the best way to go down the mountain? And you can either walk randomly, and that will take forever, or you can basically walk down like the steepest slope at every point. And so basically the gradient determines whether your loss will go up or down when you adjust the weights. So the formula to update the weight is that you use the existing weight, you calculate the gradient of the loss with respect to each weight, and then you multiply it with some learning rate, factor, and you subtract that from your current weights. Can somebody tell me why does the formula look like this? Why do we have a minus sign here instead of a plus sign? Yes.
Because the gradient shows the ascent, like going up direction. We want to go down, like minimize the loss.
Yes. So basically, the reason why we have the minus sign here is that we are going down, right? So if you think about this really simple example here, the gradient in this case is negative, right? So you multiply a negative number with a positive number and you subtract it. That means that the weights are going up. So the weights are going in this direction, meaning that your loss is going down, right? And vice versa. If you are on this side of the curve, it goes the other way. So basically, and somebody raised a question on the channel. Why is it called stochastic gradient descent? What is stochastic about it? Yes?
If we give it all the data that it had, it knows everything about the function. It's not a stochastic. But we give it bunch by bunch because of computation limitations. So every time it sees a slightly different function.
Yep.
But average of all those when we repeat it is the same as optimizing the same function. That's why it's called stochastic.
Yes. Yep, that's correct. So when we calculate the gradient, ideally we want to run through all of the data to calculate the true gradient. But that will take a lot of time. We will run out of memory. So what we do is that we feed it a small number of images of inputs at a time, and then we calculate the gradient based on that small mini batch, and that is an approximate of the true gradient. So you can think of it as you're walking on a mountain and you have 20,000 sensors and they're all a little bit noisy, right? And you're determining which way is the right way to go, and you can look at all of your sensors, and that can take forever. Or you can sample a small number of them and you think, okay, I take these 10 and whatever they tell me is a good enough approximation of what the true direction is, and then you follow that gradient. And that process can be quite random, like what you take, the sensors that you take is quite random. So that's why it's stochastic. Yep. So that process is called backpropagation. Basically, you backpropagate the error of your network down. So you run the forward pass. You start from your input and your desired targets, and you run through your network to get to the loss function, and then you calculate the derivative of the loss function with respect to all of the weights using the very simple chain rule that hopefully you still remember from high school. So that step of updating the weights based on the gradient is called an optimization step. And as we discussed before, we can either take one input at a time, or we can use all of our data in each step. But generally, we run out of time. We don't have enough memory, so we feed it. The compromise is feeding a mini batch at a time, and generally it's about 64 images at a time. So that learning rate parameter in this formula here is one of the most important parameters that you need to choose for your network, for your training. And up until fairly recently, that was a very finicky process. It was a bit of trial and error. You try a little bit high, a little bit low, and you just pick one, you know. And so these images here shows you, what happens when you pick, the different ranges. When your learning rate is too low, like you take a very small step at a time, and it can take forever for you to get to the bottom. Or when you use a learning rate that's too high, it can fluctuate a lot, and it might actually blow up. Whereas when you pick an appropriate one, then you will get to the bottom, in a decent amount of time. So to demonstrate this point, I'm just going to go to this website called Playground TensorFlow to demonstrate. So I'm just going to pick a random task and create my network. And now if I pick a very small learning rate, this is basically the loss function, and you can see that it's changing really, really quite slowly, right? Whereas if I pick a very high learning rate, it blows up immediately, and your learning completely fails. Actually, if I refresh, this is a fairly high learning rate as well. You can see it's very noisy at the beginning, and eventually it works out in the end. But if we pick a different task, which is harder, yeah, you can see it's pretty noisy. Yep, it completely fails to learn. The loss function is not going anywhere. The network is completely struggling with this. A very small learning rate. It's changing so slowly that you can't even tell. If we pick something a bit more reasonable, you can see it's a bit, more reasonable, but something funny is happening here as well. So just a difficult task. So this used to be a problem, and the problem can be explained a little bit by the nature of a high dimensional loss function. What can go wrong? Remember that our network can be made up of thousands or millions of parameters. What is the challenge of optimizing something like that? Yes. Yes. So actually, when you go high dimension, and this is only a representation of that loss function in 2D, the loss the loss function might not be smooth and easy like this case. It can be really bumpy and lots of different valleys in here, and you might be stuck in one of them, stuck in a local minimum. And that's why it can be really tricky to train deep network. So in this paper here, visualizing the loss landscape of neural nets, the authors made an observation that the trainability of neural nets is highly dependent on the architecture, on the choice of optimizer, the weight initialization, and a variety of other considerations. So it's very finicky. When networks become sufficiently deep, the loss landscape quickly transition from being nearly complex, so that way, to being highly chaotic. This transition from convex to chaotic behavior coincides with a dramatic drop in generalization error and ultimately to a lack of trainability. So this point here, it's kind of related to, again, why we should use a pre-trained model. A lot of thought has gone into designing these architectures, whereas if we design something from scratch, we might run into something like this. There's no guarantee that, our training can succeed. So going back to the topic of learning rate finder, so up until a few years ago, that was quite a hit and miss process. But the fast AI team actually made this sort of discovery of this learning rate finder function, which is really useful. So what you do is you feed your network a small batch at a time and ramping up the learning rate at the same time. And then you can see when the learning rate is small, the loss function is barely changing, and then it improves. And then at some point when your learning rate is too high, that's where it blows up, that chaotic behavior we saw before. So we want to pick the learning rate in this region here, where the loss function is improving, the steepest. And generally he recommends using a number somewhere in that region. And when we use a pre-trained model instead of a custom-made model, what we should do is fine-tuning. So what happens is that you use an existing architecture and you strip away all these higher layers and build up whatever you want, and you keep these common lower level layers, and then you fine-tune this model here. So what it means is that you freeze your model, and you only train these higher layers because they are the most related to the task what you're doing. And then after that you unfreeze, which means that you train all of the weights, even these lower ones. And two other related concepts to this training process is called fit one cycle. So you see under fine-tune, basically initially we freeze, we fit one cycle. Fit one cycle means that we ramp up the learning rate and then we ramp down. And I can't remember whether in the paper they explain why that works. Maybe it's just a trial and error. I have seen tasks where that trick doesn't seem to really help, compared to just a constant learning rate. And then once you train these higher layers, you unfreeze. So that means you train everything. And then you do fit one cycle again. Except this time you use discriminative learning rates, which means that you use higher learning rates in these higher layers. Can someone explain why that might be helpful? Yep.
Initially, as a probably really well trained, we need to shift it a little bit, but once closer to the end, need to be shifted more.
Yes.
You don't want to be messing with the first set too much. You want to have a lower learning rate there because you don't want to change the values too much so that it affects the learning.
Yes. So anyone else wants to attempt this question? Yes. So these lower layers, have been trained really well. So we don't want to, perturb them too much. And also these layers tend to be like the lower representation of the data, which shouldn't change too much, Whereas these higher level ones are more related to the task that you're doing. So you want to adjust them a little bit more aggressively. So in the second half, Tang is going to walk through a live coding session where all of these concepts come together, and you will see how it works in the code.
Can I add something?
Yep, any questions?
Why we ramp up and ramp down? The reason is when we have high learning rates, we easily go past lots of local minimals, get to the region of good solution, and then we ramp it down. We find a very good solution around that area. So with high, we pass the local minimum. With low, we find a very accurate solution.
Yes, that's my intuition as well, that you use the high learning rates to basically jump out of these local minima, and hopefully you get into a better region where then you reduce the learning rate and you explore that area. But it might well be dependent on the problem and the architecture that you're using. Yep. Any other questions? Yes?
Just one question. So we said that we want our weights to always go down.
The loss function to go down, not the weights. Yes.
Okay. So maybe I understood, but when I read that function, I thought we're always going to adjust our weights and increment down.
No, not necessarily. Yes. So the question is, do we always adjust the weights down? It depends on the gradient, right? So if you're on this side of the curve and you want the loss function to go down, you want to reduce your weights. Whereas if you're on this side, you want to increase your weights, right? So it depends on the gradient.
The differential can be positive or negative.
Yes.
Thank you.
Yep.
Got it.
Great. Any other questions? Great. Okay, I'll hand over to Tang to take over.
Okay.
Yep.
Thank you.
Thank you, Glenn. think that was really good presentation. We just cover everything about today, I guess. So in terms of the practical coding one, so I try to recreate the notebook a bit. I make sure that I can kind of explain this cycle, which is one of the most important here. And because if you see in the fast AI, I guess, and then here you can see it's quite simple. So here, this one gonna take care of everything for you guys. So which is good because it's fast. But the thing is, like, we want to know what's happening inside. So, and this is what's happening inside. Today I'm just gonna go through this one, and then we code this one together, and then we create our own model, our own optimization, and then we focus a little bit around here, and then see what's happened there as well. So,
Tim, before you start, can you tell us about yourself?
oh yeah, okay. So I'm Tan. So I'm just graduated from UQ as a software engineering. I'm doing business in like machine learning, but mainly I do deep learning in transportation, and it's just a project from government and UQ. So my PhD is mainly about graph thing, so which is really trendy and kind of frontier of deep learning nowadays. So yeah, that's this about me. So yeah, so I just today I just talk about this one. I use PyTorch because PyTorch is something, you know, can show more about the actual process behind it. So here, before we do it, we just run this one, and hopefully everyone run it. I should run this before, I guess. Yeah, so basically here we're gonna have a look at the 10 digits classification problem rather than just 3 and 7. So because we use PyTorch, so I think it's gonna be more convenient to just download the dataset from PyTorch library. Yeah, it takes a while, I think, probably 5 minutes, 5 seconds, not 5 minutes. So here you can see it's like we have a dataset here, just downloading it, and then yeah. So have a look at this cycle. So firstly, we initialize the weights, and then we have a model already around there, for example. Then we're gonna use the model to do the forward part. We predict, we get the result, and the result may be in the middle of this one, and then we calculate the loss based on our labels. And then we calculate the gradient, and then we update the weights, and then we repeat the process, and then we stop when we need to stop, I guess. Yeah, I think it's already there, so this one we don't need to go through. So here I just print the first sample of the dataset, so which is 5, the image of 5. You see here I saw the subalgebra 28 by 28. I saw the test one. I just get the target. This is weird. Shouldn't be target, right? No, target. Yeah, target. And then we done this one, so the label. Then we saw the sub of it. We have 60,000 sample, and then up 28 by 28 images. Yeah, and then we just resub the image into one single vector. Yeah, and then we just double check the dimension of the vector that we just recreate. I think, yeah, just quickly go through this. We check the type, So one trick is here, like usually PyTorch is work better with float number. So we just refer to transfer it into float number. Yeah. So here I have a normalization step as well. So usually PyTorch, they have some data loader or even fast.ai, they also have, but here I just want to highlight that we need a way to normalize our data. And like, do you guys know why we have to normalize our data? Something? Yeah. Yeah, yeah.
Yeah, it's usually so, depending on what you're doing, but it's so that outliers can't have too much effect on the training. So you perhaps put together between more and one.
Yeah, yeah. So that's a correct question. Correct answer, because usually when we have different cap features or attributes for one images, we're gonna have different cap dimensions, like interval of the value, and we need to make sure that everything in the same range. Yeah, that's why here I just simply normalize them, just using just normalize equation, I guess. So we just calculate the mean here. Yeah. Yeah, and then here I just double check the data set again, so make sure that we have here we have Y training, we have unique, and then we have 0, 1, 2, 3 until 9 images. We have this one as well, they are 10 classes. Yeah, so here we gonna have a look at the file model here. So if you see at the slide, there's gonna be a I think here there's gonna be a sample net. So where we have one linear layer, we have non-linear layer, which is ReLU, and then we have another linear layer, and then we just stop there. So which is our simple net. So here, if you see in the PyTorch, there's a different way to create. So here I just use this one. So hopefully people familiar, because I think Jeremy also mentioned in his lecture is about linear function. In PyTorch, they just take care of everything. So what do they take care there? So here when they do you guys do this one in PyTorch, they just initialize the weights, create the kind of linear equation for you guys. We have the weights, we have also bias here as well, so which is equivalent to this line, and also initialize the weights at the beginning, so we don't have to do all of them. So yeah, can anyone tell me like what should I design this kind of layer? So how many input like unique I should get? Because remember, we just flatten the images into one single vector. So yeah, so here we have 78.4, and we want to get out. This is just depend. Some people can just out feature. You guys can see here we're gonna have out features, and then we have probably 30 or maybe some other number if you guys want. Here we have nonlinear one. So and then yeah, I think you guys can create another one at the end. So it's gonna be nn dot linear as well. Then we have, I think this one should be 28 by 28. So because encoding is good to show that why you have 78 and 4, 78 and 4, right? Yeah, so because we multiply the dimension of the images. Oh. Here we have linear as well. Linear, and then yeah. Can someone tell me like how should I put the parameters in this? Yeah, because remember we have one linear to map the input from 28 multiply 28 to 30 output. So yeah, 30. So that's correct. So even we put it into the ReLU, we have 30 there. How about the output? Like,
Number of categories.
yeah, so can someone tell me like why we want it to be the number of the category? Yeah, because in this case, yeah, I think just simply because it's the last layer and because we want to stop there, so that's why we just put 10 there because we have 10 labels there. Here in PyTorch we have just create model equal and then dot sequential, I guess. Then here, this one I'm gonna just and then we need to have column there as well. And that's it. Yeah, now we have our model which represent this one and also initialize the weights. Now we just run this one. Hopefully we don't have any error. Yeah, that's good. We don't have any error. So here we can, yeah, we have to input our data into it. So here, if you guys, we have output and then we just simply call model. So because the data I just get here, here's the data where we have 60,000 samples. So we just put there. So for one sample, we're gonna have 28 by 28, 28 multiply 28 length, the length of the vector. And then we run through it. And then we doesn't really get anything because we need to print. Okay. You see the sub of it. So here we get 10. So here what does mean? So our output is 60,000 samples, 60,000, and then for each output it's gonna contain 10 different values, and each of them gonna represent for each category. So yeah, just print one, and then you are gonna see the output is called random. So we have negative, we have 0 point something and 0 0.7, yeah, really small and also really big one. So here they are not really the actual probabilities, so that's why we need to have a look at the loss one. So here, as Huynh mentioned, in our case, we need a cross entropy loss. So yeah. So can anyone tell me like how can we do cross entropy in PyTorch? Yeah, okay. So I think yeah, here I just output. I think in my notebook I just output the same thing. Probably I change it to 1. So we have cross entropy. Basically we just hop that cross entropy. The output is just like we want all the probabilities of the outputs gonna sum into 1. So this is what we want. This is what we call actual probability, so that our model can be easily learned. Yeah, so here we have maybe cross entropy loss. Then we equal, we have, and then dot cross should be here, the collab just mentioned. Then we have cross, and then we have loss. Then loss equal cross loss. Here we just get the output from the model, output model, I guess, and then we compare with the target. Yeah, hopefully we have the target is here we store on the target of the training set into the y underscore trend. So here we just y underscore trend instead of target, but we need the output from the forward part. So here we have this one, we have model, we have output model equal our model just create, then we get the we get the trend one. Yep. Then we run this one, then we get nothing simply because we didn't print anything there. Okay, here we get something there. So this, the whole thing like this is gonna present for this part, like we initialize, we predict, we calculate the loss, right? But we just like this, but this one we have the whole like iterative process as well. So how can we do that? So here we have a look at this one, we have a training loop there. So here we have to figure out how to build this cap circle, right? So we have initialize, create, predicted, get the loss, and also now we need to calculate the gradient, and then we repeat them. Yeah, so I think most of you guys probably seen, like, I hope you guys just watched the lecture before and then also see this one in from the video. So we in the video Jeremy created the basis optimizer, but we're gonna have a look at this one later because I think it's better to have a look at the higher level than the lower one. So here we can see, instead of using the optimizer there, we just use the optimizer from PyTorch, I guess. So here we have torch.optim, and there's some ADAM one. And we also do the same thing, we part parameter, then we part the learning rate. We don't have learning rate there, just create learning rate equal 0.1 for example, and then we have maybe later we pass the learning rate there. Yeah, we have arrow. Yeah, okay. Now we just assume that we have the optimizer already. We don't need to care about what's inside the optimizer. We're gonna have a build our own one later. So here we have the learning rate. So now we want to build this kind of iterative process. So just build a for loop, and then maybe just I in range. Maybe just 50. And then here we have a loop there. So can anyone tell me where should I calculate the loss in this loop? Okay, so here we have the loop, and then we need to do a forward part. which is this one. We predict, we have the model there, right, around, just imagine it should be around there. And then we predict, and then we get the loss. So which means this area and the other like loss part as well should be in the iterative process. So here you are gonna have, we need to get the output of the model from the model, equal model. And again, we have our training data equal input and our labels equal target. Yeah, and we pass the target 1. So can someone tell me what should I do next in terms of this process? Yeah, so here we just calculate the loss because we already have the loss function created. We calculate the loss in the same way. So up here we have output, then we have target here. So because here we have optimizer again, we call optimizer because the gradient every time in PyTorch, the gradient gonna like every time you guys train like do the forward part, they calculate the gradient, right? So here you have the gradient here. So in PyTorch, most of, I don't know, but mainly in PyTorch, I guess they're gonna keep the gradient here, and the next time you do the forward part, the gradient gonna be still there. So it's just at the result, as a result, you guys gonna have, you know, like the really big gradient from the previous step. So here we have to get the gradient equals 0. So we have 0 gradient here, which is do some magic thing. Maybe just get it into equals 0. And then we have loss part. Then we update the model by using step. Then because we should print the loss, right, to see what's happened here. So here basically we just do this part, predict, calculate the loss, then we set the gradient from the previous process equal to 0 because we don't want to get from the previous process. So here we just do the loss thought part to get calculate the gradient, and then we do the last one's optimize dot step to kind of update the weights. So I think Jeremy already covered this part in the video as well. So here just quickly do like this. Oh, we have arrow, so just here. And then we expect that the loss to be, you know, like decrease over time. If it's decrease, so there might be some problem there. Oh yeah, just this one should be 1 only, sorry. Yeah, and then it just decrease over time, so you can see. Yeah, it should just decrease, that's good. Sorry?
Can we make that 500?
Yeah, so yeah, basically we can make it 500. Yeah, so for here we have a, so here this 50 should be called as a airport, right? Because we go through on the data set as one, so just airport equal 50 here. Yeah. So this is the whole process, and then we just again, right? Michael just said we go forever, and yeah, at some point we should stop because in the previous lecture from this course, I think Michael already said, you need to figure out when should you stop the training, like by using validation set and the testing and validation and the training set, then compare them like how many airports you should go, right? So airports here also one of the pretty important hyperparameter because it takes time to run it. So
Could you not just iterate through till you are happy with the loss and jump out?
the question is that when will you happy?
Yeah, that's
Right, yeah. So yes, like Michael said in the previous lecture, have some kind of like before you overfitting the model and also like after before you underfitting the model and after you overfitting the model is the best point to stop. Yeah. So here we have something like this one. And because we don't have so many times, so I just quickly go through this one again. So here so our big question is that what happened in the ADAM one, right? Like whatever, we don't need to care about now, but how about we create our own optimizer? And Jeremy created one in the video. So here we have the depth, and then we just have we in it. So I hope everyone familiar with this. So we have we have a class, we have params, and we have learning rate. Then we init like just params. So the params equal list because we means many. Here, so the colon race. Yeah, it's correct. And then here in this one we should have order method, which is this step, and also depth 0 gradient, right? Then we just pass some parameter there. We have argument. We have argument there as well. Then we copy there. So here, if you guys see, we in the item they also have 0 gradient and also have the step 1. Right. So for 0 gradient, can someone tell me like what should we do there? For 0 gradient.
Set the gradient.
Yeah. Yeah, that's correct. So we need to set on the gradient into 0 there. So we have 4 probably parameter in cell because we have params there. So the first kind of parameter of this optimizer gonna be the parameters up here, model.parameter. So here we're gonna go through all the parameter, and then we graph and just equal to none. Yeah, so for this step, so we update again. We need to go through all of them and prompts. Yeah, so can someone tell me what should I do there? So how this method gonna update the weights, the parameters?
Plus learning rate and
You mean plus or minus?
minus.
Yeah, it should be minus, right? So Huyên already explained the reason why we need to minus this. So here we have graph, and then we minus data, and then we multiply learning rate. We have Yeah, I think everything good now. We have cell dot for what, and then we just no arrow. So here we just go there. Instead of using this one, we use our own optimizer. We have basis of team, then we get model dot parameters. Then we have learning rate. So yep, on good now. Then we run this one again. Hopefully it's decrease again. Yeah, it's not so good. So probably it's, yeah, but it's still decrease. So the reason it doesn't decrease that much here because we already trained our model a little bit. So if we need to go up there, just reinitialize our model. Yeah, hopefully. Then we go down there, we do this one, and we run this again. Yeah, it's so a little bit clear. Yeah, so now finally we have implement the whole cycle there. So here's another question, like kind of how we can do it, like just a patch at the time rather than the whole data set. So I let this one for you guys later. Yeah, I just let this one for you guys to try later by yourself, or maybe just talk with me. So the process is kind of exactly the same. So here we just go through a patches at a time rather than the whole one for every approach. Yeah, and then here finally we just simply use some data set like the deeper model in fast AI to kind of so here we just get the data. We have URL as, and we have image sample there. Then we create an image data loader object from this dot from folder, and we have something there. Yeah, here, and then we just create another CNN learner. We pass this OS, then we use the redness one, like in the slide. Then we have pre-chain, just for. Then yeah, we have load function as well. Should be equal to app. Yeah, and then we have matrix equal accuracy. Then we run it. Yeah, and then we just use learn dot fit one cycle and then see how it's work. We need to pass parameter the learning rate here. We have number of the airport. We just run one time. Yeah, as you can see, it's like here we have a deeper model, and then it's gonna take a little bit more time, probably. Yeah, we already used. So yeah, the resonance is far more deeper than our simple model, so take longer a bit. Yeah, so I think that's it for today. So if you guys have any question about this part, we can have a look, but it should be easy because we just basically do the same thing. us do the past one, and there probably some minor problem. Yeah. Okay. That's it for today. Thank you. Awesome. Thanks so much. It's following you. Thanks so much, Gwen and Tan. That was awesome. Yeah, really good slides, some good pictures and visualizations in there. And yeah, I mean, a lot of this course is about sort of jumping straight in and building models and, you know, getting a model pretty quickly without having to dive into the weeds. But once you do spend a bit more time training models, and you do have to start diagnosing things and trying to figure out how you're optimizing it, you know, understanding what's happening under the hood, being able to understand what's happening as it's propagating losses and understanding the gradients becomes really, really handy. So, you know, this is sort of a little bit of a taste, but definitely encourage you guys, once you are feeling comfortable, to start to go back and dive a little bit deeper to learn a bit more. So that's all for this stuff at the moment. If you do have questions, feel free to hit our mentors up. For now, what we'll do is we'll probably switch into our groups, and you guys can catch up and talk about your projects and keep moving forward. A couple updates on that note. There's been a couple more groups formed. There's quite a few people, and I did have a look at how many groups we do have with sort of less than 3 people. I did note also that as I was looking at those groups of only 1 or 2 people, a few of those people and groups have actually come up to me and asked me if you guys can work on your own problems with your own data, clearly motivated to work on them. So it's kind of like I didn't actually want to then go and, you know, say that, look, you can't work on that. So I think what we'll do is we'll run with all the groups as we are. You know, as we've done this course before, we've noted that, you know, people do tend to drop off. As much as we don't want that to happen, I'm sure, you know, there will be a little bit of moving around in groups. Hopefully that's not you guys. I really want you guys to stick with it because it is worth doing. But I don't think there's been too much of a workload so far on the mentors with managing everyone. So I think as far as groups goes, we'll leave things as they are. If you are struggling with your group and it is down to 1 or 2 people, feel free to message one of us. If you do want to then merge with a different group, we'll be able to do that. For now, I think the only other thing that's worth saying is what we will do probably in the next 24 hours is basically start sort of assigning mentors or groups of mentors to groups. We are still toying with the idea of whether we have individual mentors assigned to sort of a couple groups. The only issue there is that if a mentor needs to go on leave for a week, you know, you might be without a mentor. Maybe we have a couple. The other idea would be maybe having a group of mentors, so all the NLP mentors, and then all the NLP groups can basically tag an NLP mentor, and then whoever's online that day or you know, at that time can sort of hop in to any tags that they've been tagged with and sort of answer those questions. So that might be a nice middle ground. I'll have a chat with the mentors today and then put some instructions tonight in the announcements channel to let you guys know how you can get help. Sounds good? Cool. Any questions, guys, on this or the groups or anything else, or anything you guys are having challenges with that you want to raise? Cool. Sounds good. Everything's smooth sailing. Great. All right. Let's move into our groups and yeah, keep moving ahead. The only thing that I would say is that, you know, we are a week in now, so I think if you guys can make sure that you all have a pretty clear idea of what you're working towards, your strategy, I would definitely encourage you guys to start setting some milestones of what you'd like to achieve week by week. So that you can make sure that, you know, everyone's contributing and you're making good progress, but, you know, so that you can actually plan ahead to what that final showcase looks like and make sure that you've got something you guys are proud of. So I might actually dig up a previous slide that sort of shows, you know, some examples of where you might like to be by each week, and you guys can maybe plan to sort of follow that same sort of cadence. Cool. I'll put that up on the board and feel free to spread around. Awesome. Thanks, guys.
We can talk
All right, everyone. Thanks for coming. Have a good week. We'll talk more in Discord. Thank you. See you later.